Okay, this is lecture number 8. Any questions? So I assume now at least the acquisition and locking of the PLL with the given phase detector is something which you understand. And on the same lines, you can actually analyze other kind of PLLs also, right? Okay, so let me just redraw the block diagram of a PLL, and let me say what we are going to do next. Okay, so we have input V in, where we want to consider only phase input. Output is voltage signal V out, but we are looking for phase at the output. Okay, and we have phase detector, loop filter, and oscillator. Okay, so this is the block. So what we have seen is like a typical PLL. Type 1, order 2, type 2 and order 2. This is something which we have seen so far. Okay. Now the phase detector which we have used so far is a sinusoidal mixer based phase error detector, and it's not that this is the only phase detector. There are other phase detectors also. So now we will go into each of these blocks and define some kind of characteristics of at behavioral level. Okay, we will look at the circuit level after the behavioral level simulation and the block functioning. So we will start one by one. So first one is phase error detector. We write it as phase detector also. Okay. So this phase detector normally are of two types. These phase error detector blocks. One is analog PD. And the other one is digital PD. Okay, so we will see what this analog and digital PD are. Within analog, so what is analog phase detector? It is going to operate on the analog, on the signals, whatever the input signals, which is V in and V out. It will find the phase error, and the phase error, whatever value you are going to get, that will be the proportional to phase error. Okay. Now it is going to operate on analog signals as such. So here, let me just draw the block diagram. So normally you will have two inputs to the phase detector because it tries to measure the phase error between two signals. So this is V in and V out, and the output of this phase detector, whatever this V error, this should be somehow related to the phase error between the input signals. That is the requirement. Okay. And what we have seen is mixer based phase error detector, so that comes under analog phase detector. So I have V in and V out. I think this is something which we have been seeing since day one. So for V in equals to A in times sine of omega in T, and V out is equals to, let me just write, this as A out sine of omega, or let me, in place of writing omega in, let's assume that they are the same frequency, because right now I am only considering the phase error, omega out T minus delta phi. If this is the signal, then V error is equals to half of cosine of delta phi minus cosine of 2 omega naught T minus delta phi. Okay, this is the output of the phase error detector. Now the average of this phase error detector is equals to half times cosine of delta phi, where delta phi is the phase error between the input and the output. Two input signals, V in and V out. I am writing V out because this is just a feedback signal from in the PLL. Otherwise you can write V1 and V2. Okay, so now this phase, if you look at the phase error detector output characteristics, you will find this is cosine function. Okay, on y-axis I am plotting phase error delta phi, on x-axis, and on y-axis this is average of the error voltage. Okay, and I think this everyone will understand that if I take the average, the high frequency part will be reduced to 0. Okay, now what is this phase values? This is minus, so I have, is there anything wrong? No. Okay, so this is minus pi by 2, this one is plus pi by 2, and plus 3 pi by 2, and so on, minus 3 pi by 2. Okay. Now you see that the output of this phase error detector, first thing, it is non-monotonous for a given input phase error. Okay, it is non-linear also. So if I want to use this in a just looking the PLL for any feedback loop, if I want to approximate this as in a negative feedback always, which section of this phase error detector would be useful for you? So the question, let me repeat the question. You see that the phase error detector output is non-monotonous, it is non-linear, and I am using this phase error detector in the PLL. I want to have a negative feedback. Okay, so if I want to have a negative feedback, which section of this phase, means on the phase error on x-axis delta phi, which range of this phase error detector is useful to ensure that the PLL is always in negative feedback? It is not going to be in the positive feedback or no positive feedback inside the PLL loop, depending on if the phase error shifts slightly. Minus pi to, so minus, why it is minus pi? Okay, how many are from minus pi to 0? Okay, how many are from minus pi to 0? Why you change from minus pi by 2 to, so I am asking two things, minus pi by 2 to 0, and the other one is minus pi to 0. Okay, so this two TO2 and divided by 2 are two different. Okay, so which range do you think will ensure that, which is the largest range you think will ensure that you are always in the negative feedback? Minus pi to 0, this one, right? So I can always use, I can say that if my phase error is within this range, minus pi to 0, then the PLL will always be in a negative feedback. The feedback will not change the sign, and it will always try to bring the output close to the input in the feedback loop. Okay, if you go in this direction, then the feedback sign is going to change, right? So it's normally defined as a linear range. It's actually not linear, but it's a non-monotonous, not non-monotonous, monotonous range is minus pi to 0. Okay, now the thing is, this minus pi to 0 is the range I can, means just for my easiness, I can have a shift in the variable and say, let me just write delta phi of set, or delta phi in a steady state, where I make a change in the variable that delta phi s is equals to delta phi minus pi by 2. Just a change in a variable. Then I will say that my range is minus pi by 2 to plus pi by 2. Okay, this is just a change in the variable. so that you can see, okay, you are centered around 0. Okay. Why did I do so? You can also think that if the PLL is going to log, where I have a 0 frequency error at the input and output, like omega in and omega out, both the frequencies are same to begin with, then the PLL should log to a 0 frequency error, 0 phase error in a type 1 PLL, right? If I change the positive frequency, it is going to log to a positive phase error. If I give a negative frequency error, it is going to log to a negative steady state phase error. Okay, that's why I always try to consider this centered at 0. Yes. Where plus pi by 2? Okay, let's say this is delta phi plus pi by 2. Fine. Okay. So this is the monotonous range is minus pi to 0, or you can also say minus pi by 2 to pi by 2. Okay. What is the gain of this phase error detector? So the gain of phase error detector will be defined as KPD. So I think that we have seen this, but just for completion here, gain of phase detector KPD is equals to derivative of average phase error, average output of the phase error detector by phase error itself, which is equals to, this is half of sine of delta phi. No, it's a function of delta phi. The gain itself is a function of the delta phi. I'm talking about the gain only, right? It's a non-linear. I'm not saying it's a linear from minus pi by 2 to pi by 2. The only thing I am saying, it's monotonous. It will maintain the negative feedback. If you go for a positive phase error, it will have a positive gain. If you go for a negative phase error, it will have a negative gain at the output.
So is there any way to find whether
no, so means okay, whether, so let us say if I started in place of sine, I started with cosine, right? What will have? This curve will just shift. Okay, nothing more, it will just shift. So that's why I told that for a 0 frequency error between the input, between the two signals, V in and V out, for the phase error detector, if there is 0 frequency error to begin with, right? What phase error should it log to in a steady state for a type 1 PLL? 0, right? If you give a positive frequency error, it is going to log to a positive phase error. If you are going to give a negative frequency error, it will log to a negative phase error, right? So this is just a convention, right? It has nothing to do with the means. Your PLL may actually be operating, if you are doing this sine and cosine, it is going to log with this way only. Okay? And the input and the V in and V out signal will log to a phase offset of pi by 2. So if it becomes pi by 2, this will be equals to A out times sine of omega naught t minus pi by 2. So what is minus sine of 90 minus theta? This will be equals to A out minus ASTC, right? So cosine of omega naught t. Okay, in a steady state, the phase offset between the input and the output signals is going to be pi by 2. Okay, if the input frequencies are same, right? Now, if you want, let us take, so for a type 1 and order 1 PLL or type 1 and order 2 PLL, do you agree with this part? Okay, now if we take, let's say, type 2 PLL also, if the frequencies are the same, the control voltage which is required is 0, right? Now what the phase error should be? So I am talking of this thing. So for a type 2 PLL, I have gain block tau p over tau I and 1 over tau is, right? This is something which goes in the VCO. Okay. Now what I want in the control in a steady state, if the free running frequency of the oscillator is the same as the input frequency, means omega out is equals to omega in for control voltage equals to 0, right? The phase error is, this is also is going to lock to a steady state phase error, means error voltage here should be equals to 0, right? Which means this PLL should lock to a, means if I am considering sine, if this is a mixer based phase error detector, it should lock to a phase offset of pi by 2. Okay, and if you remember, the locking condition for a PLL is not that the phase error is equals to 0. The locking condition for a PLL is the phase error should not change with respect to time. Okay, if I have any kind of a positive value here, just for an example, I can have means V error voltage some delta V as a positive value. Right? If the free running voltage is the same as the free running frequency of the oscillator is same as the input frequency, then I should get a negative component from the integral part, such that VC should be 0. Do you agree? This is a little bit confusing for you, so let me just say my VC is equals to VP plus VI, right? The error which is coming from the positive part, the error which is coming from the from the proportional path, and the error which is coming from the integral path. If by force I say that VI is some positive value, VI is just, let us say, delta VI, fixed positive value. Okay, then for that delta VI, VC should be equals to 0 for the PLL to lock in steady state, because that's the voltage which is required to have the same frequency. So this is equals to 0, so VP will be equals to minus delta VI. Okay, now in response to this VP voltage, you are going to have a error voltage corresponding. So these things will, what voltage you are getting at the output of the phase error detector will also change depending on what is an offset you are getting in the integral part. Okay, so this is something, some way in which you can manipulate the voltages and phases. So if I have some kind of positive, now you see, if I have this VP as some negative voltage, then I should have some phase offset at the input, and that will also be the lock condition. So for locking, it does not require that you should always have a phase error of 0, but you should have, the phase error should not change with respect to time. Any confusion you have? It's a non-zero, it's not changing. I know that someone will pick up. If you have a if you have a non-zero value at the input of the integral, then that integrator will keep on rising, and let's say it has saturated. Let us say the integral has a finite gain, means what you are saying is right. If I have this as a pure integrator 1 over S, then there is no other condition other than V error average equal to 0. There is no other condition. Okay, but if you have for a same frequencies, okay, but if you have some kind of a limited integral, means if you have a finite gain in which you are implementing this integral, then you will have some finite value. With respect to that, you will have a V error, and then you can have the corresponding phase error. Okay. Any other? So this phase detector gain which we worked out, this is a non-linear phase detector gain which is varying all the time. So you can plot this minus, means I can plot, this is also sinusoidal. So with respect to delta phi, I am plotting kpd. This is minus sine phi. So this is going to be like this. Okay, and if you remember, I am considering my phase error detector in this range, pi minus pi to 0. So same thing, where is it? Minus pi to 0. So my phase error detector gain, the range which I am considering is only this. Is it right, or is there anything which I am missing here? So my average phase error detector output is equals to half of cosine phi, and differentiation of cosine phi is sine minus sine. So this is kpd. So you see that the gain of the phase error detector is changing throughout the range of the phase error, which is completely non-linear dynamics. Okay. So whenever we write a linear gain of the phase error detector and we are using this particular mixer based phase error detector, we should be aware that the kpd is, whatever value we are using is valid in a very, very small range. Okay. Now there is another analog phase error detector which is sampling based or sampler phase detector. Okay, what does it do? So here, so let me first ask you this. So let us say I have this, again the input signal is analog. Okay, so this is my input signal, and with respect to time, let me just mark that this is equals to V in, and I want to measure a phase error with respect to another signal which is also periodic. Okay, I am measuring phase error with respect to a periodic signal only. So if I sample this particular sine wave with the same frequency as the frequency of this sine wave, okay, using another clock, for example, let us say my other clock is this. Why I chose one sinusoidal and one rectangular means that this is just for an easiness. So let us say like this. Let us say this is my V out signal and V in is shown as in black, and I am sampling my V out with respect to V in, and the period of V out is also same as T. Okay. So whatever the block sampler based PD, there is some block which takes two signals V in and V out, and the output of this I am calling this as V error. Okay, this is sampler based PD. So what is the output of my this phase detector? VE is equals to whatever my A in times sine of, let us say this is omega in times T. Sorry, this is my V in signal. Okay, and what instant am I sampling? So if I have a delta T phase shift of the sampling clock with respect to the input clock, then my V error will be A in times sine of omega in of n times the time period plus delta t. Okay, so the output V error, if I look at the V error output, will always be, is a sample and hold circuit I am having, so this is always going to be same. So on. Okay, so this is equals to V error is equals to A n times sine of omega in n times omega nt plus omega n times delta t, and this part you know this is equals to n 2 pi. So this is equals to A n times sine of omega n, I can let me just write it as delta t over t, which is also equals to A n times sine of delta phi. Okay, so now this particular phase error detector also has, so the only thing which you are right now seeing is that this phase error detector has only one component, in contrast to the previous phase error detector which has both 2 omega and we looked at the average value, right? Here if the two frequencies are going to be same, then you have a constant value. Okay, how can you implement it? It's very easy that I can have a sampling clock and maybe with some gain, and this is my output, so this is my input signal. My output signal is sampling the input, maybe with a capacitor, some capacitor here, and this is my V error. Okay. Now, if this particular V error is a function of the phase error in this manner, then what can you comment on the monotonous range of this phase error detector? I can very well write this is minus pi by 2 to pi by 2. V error. Okay. What about the gain of this particular phase error detector? The gain is equals to KPD is equals to derivative of V error with respect to delta phi. This is equals to what A n times cosine of delta phi. Okay. The gain is non-linear for this phase detector. Okay. Why am I focusing so much on the gain of the phase error detector? Can someone tell me? It's non-linear, so what's the problem? The PLL is still locked, I have shown to you, right? Many of these PLLs, they lock with the non-linear gain also. So, why do we need to know this part as such? Huh? No, I have done all these. It starts with the when this PLL locks with any given frequency error, it goes through all kinds of gain, right? And finally it locks. Why do I need to know this gain at all? My PLL is locked, so for all the small signal analysis, you need this. Is like an operating point analysis. You do an operating point analysis for a transistor, right? When you use it in a common source amplifier or something, it's the same thing. Once everything locks, you need to find the small signal gain of each of the blocks to analyze later for the noise or any small disturbances in the system. Okay. Now, what happens in this? So you have surely seen, yes. Sample and hold, right? So if I just look at, so means yes, you can say this is going to be the track and hold, but I am actually sampling this value, and I just sample at one particular instant. I can do that also. Okay. Surely means what he is saying is the way I have shown you this particular switch here, right? I am actually tracking for this whole, let me just say, if this is the case, I am tracking for this whole time, whatever the value it has, and then I hold that value. Okay, this is what he suggests, but I am saying I can do this, that I just sample at that point and I just retain that value. Okay, that is actual sample and hold. If I just use a single switch here, there will be a track and hold. Okay, how we will implement it, we will see that thing later. Okay. So the thing which you should only take from this kind of like signal waveform is that I sample at one particular point and I hold for the whole period. Okay. Now, what? Yeah, so the sampling point is only the delta t time shifted from the pi by 2 phase, right? Huh? Yeah, I'm sampling only at rising edge of the clock. I'm not sampling at the, means if I just have this V in and the switch and this capacitor, the actual waveform will do as I have told. It will come here, and when the switch is off, it will hold. Then again it is going to track. That's a track and hold it will, but I am trying to just sample it and take the value. Okay, now what happens if you are having any frequency error? Means this is just for the adding to this phase detector. If I have any frequency error, so you have seen for a mixer based phase error detector, you have seen that if I have any frequency error and I am trying to get this phase error detector in open loop, then the V error voltage was doing some kind of asymmetric beats, whatever, depending on the frequency error between the two. Right? Now, what will happen in this case if I am still pursuing the same sample and hold for the this phase detector? So you may keep on sampling different points every time. Maybe then again the point comes back as lesser, some lesser value. So you will have for a given frequency error, you may have some like jumps, and then you will have a varying value at the output of the phase error detector, which will represent to the frequency error in some range. Okay, it does not say that it is always linearly proportional to the frequency error. It is just proportional to the frequency error. Okay. Now, this is the, when I told that if I am sampling the input signal with another clock signal which is at the same frequency. Okay. Now let me introduce another kind of, means this is a part of the sampler based phase error detector only. If my sampling frequency is much smaller than my, so let us say this is my output frequency, or this is my the faster frequency. So let me just say this, I am calling this as V out. Okay, and I am sampling with a clock which is, let us say, 2 times lesser than my input V out frequency. So V out, let me call this period as T out. Okay, and my sampling period is half of the twice the V out period. So if I am sampling here, then the next point which I am going to sample is on the second clock, means another, okay, then I sample here, and then next I am going to sample at this point. So my sampling period T sample is equals to 2 times T out. Okay, this is just an example. So what it means is my F out, means this will imply my F out is actually equal to 2 times my F sampling. Agree? Now let me write my output phase detector. So let's say this is my V in signal, so this is V in signal and V out signal. I am sampling V out with the lower frequency signal V in, and I am looking at phase error. I am telling you that F out is equals to 2 times F sample. I am enforcing somehow, right? Then my V error will be A out times sine of omega out times T plus whatever sampling. What is my sampling time? My sampling time is n times t sample plus delta t, whatever the offset is from the zero crossing, right? Now this is equal to A out times sine of n. Omega out is, let me just write omega out in terms of t sample and t out, plus omega out delta t. Okay, so what is this value? Sine of, let me write 2n pi. What is t sample by t out? 2. It's an integer, right? Here. And omega out is equals to 2 pi, I will write delta t by t out. Okay, so this will be equals to A out times sine of 2 pi delta t over t out, right? And this is, I can write A out times sine of phase error delta phi. Okay, so couple of observations here, that I am sampling my higher frequency signal with the low frequency signal, right? This is called as subsampling. Okay, the phase error delta phi which you are looking here, the delta phi phase error is with respect to higher frequency signal here or lower frequency signal here. And what is this? Higher frequency signal, right? So phase error is with respect to the output signal here. Okay, and so let me write this here. V error is equals to A out times sine of delta phi. You can even use this phase error detector when the frequencies are like integer multiples here, okay, and you can log for a zero phase error also. And such kind of PLLs normally are called as subsampled PLLs, where you use this kind of phase error detector. Okay. So now another important thing you look now. If I just plot this particular phase error detector with respect to delta phi, you see that this is A out times sine of delta phi, means this is going to be the from minus pi by 2 to plus pi by 2, this is V error. Okay. Interestingly, this particular, or let me just put all the points, this is 2 pi. This 2 pi phase error corresponds to how much phase error in time? Means this corresponds to a phase error of, means that in terms of time this is t out. Okay. Now let us say I increase the frequency by 4 times, output frequency, and I am using the same sinusoidal, means this subsampling based phase error detector. Then and I plot with the means all this delta phi which I am writing here, I can also write in terms of delta t. No problem, right? Delta t for a phase error detector when my output frequency is 2 times the sampling frequency, then the phase error output is like this. But if my output frequency becomes 4 times the sampling frequency, in that case this will be my phase error detector output, right? With respect to delta t, don't look at delta phi. Agree? So in terms of the phase error delta t, what happens to the gain of the PD if my output frequency changes? It does not remain the same. It varies, right? And in terms of absolute times, if we are going to analyze this in terms of time error in the PLL, what you will find that the gain of the phase error detector varies with respect to the output frequency here. For the higher frequency, like if the output frequency is higher, means if we can consider two cases, F out is equals to N1 times F ref, and F out 1 and F out 2 is equals to N2 times F ref. If N2 is greater than N1, then it implies that the gain of the PD in case of N2 is going to be higher with respect to N1. Okay, and we have not yet looked at clock multipliers, which typically means that I am going to have means that in a clock multiplier you have a divide by n on frequency in the feedback loop, such that the two signals which come at the phase error detector, they are in locked state, they should be of the same frequency. Okay, so if I mean this is I am just introducing here, when you have a divide by n in the feedback loop, it is not dividing the voltage first, it is dividing only the frequency, where F out is equals to n times F in. Okay, and the loop gain of this PLL is going to be your KPD whatever you have times F of S into 2 pi k VCO over S into 1 over n, because the phase also gets divided when the frequency gets divided. Okay, now this is a conventional PLL or typical PLL which we use. Now if I am using a subsampling PLL or as a subsampler based phase error detector, where I am sampling the output frequency with the reference frequency, I do not need this divide by n. Now if you have a question that who enforces that this relationship should be n, maybe some other loop. But within the PLL, when I am correcting for the phase error, I do not need to worry about the frequency error. Right now, I do not have any divide by n in the PLL loop. If I do not have divide by n in the PLL loop, what happens to the loop gain? It increases by n times with respect to the conventional loop. So you will see what this loop gain play a role when we look at any of the subsample PLLs for the regular PLLs. Huh? How do you define it as faster? Means this is something which we need to look a little bit in, because this loop gain is when the PLL is locked. So a lot of time to correct may not be the right thing. Okay. So the thing is, we have not yet looked at the noise in the PLL, what kind of bandwidth requirements are on the PLL, how are we going to implement loop filter and KVCO, right? I may have a 1 by n factor or may not have a 1 by n factor, but I can still enforce the same loop gain for the two different kinds of PLLs. I have freedom for the loop filter KVCO, right? So that is not what we are, we can say it is faster. Faster depends a lot on the bandwidth of the PLL itself. Okay, the only difference which I want to point out right now, that by using a subsample based phase detector, the big difference which it comes is no divider in the feedback loop. That's it. Okay. So these are the two different analog based phase error detector. Then we have to look at digital phase detector. Okay. So in digital phase detector, we will mostly operate with the digital input signals, and these digital input signals means the two signals which are going to the phase detector will be clock signals only. Okay, so this phase detector, the input signals are clock. So whether you write V in and V out, or you write means single. So far we have been using V in and V out because we are writing them as a function of time. Both were sinusoidal, or one of them was sinusoidal. Now I will just to make it more simpler, I will just use R and V. These are the two digital clocks which are coming to the phase detector. Okay, so let us see what these signals are and how are they different from V in and V out. So now I consider two signals, clock signals, R and V. Okay, this is R, and the other V signal is somewhat shifted from the okay. So this is delta T, the difference. Okay, now all of us know that this R and V signal, if it is periodic in some time period T, you can write the Fourier series of this signal with sinusoids, right? But here we are not going to do that. Okay, we will only consider what is the difference between the either the rising edges or the falling edges between these two signals, and that is the phase difference between the two signals. So to you it might be slightly confusing that so far I was considering the two sinusoids, right, and I was considering the phase error with respect to phase error between these two signals at any given instant of time. Okay, I did not limit myself to any particular instant. I said, okay, this is what it is for all the time. But here we are only considering with respect to these edges. So this is the time difference. Okay, and this for R and V signals, the phase error which you see here, delta phi is equals to 2 pi times delta T over T, if T is the time period. And here the time period of the two signals are same. This is what we want to measure using the digital phase detector. Okay, so one of the blocks which can do that, let's see, is an XOR block, and it is called as XOR, exclusive XOR gate based phase error detector. So let me write, this is V times PD. Okay, the output of this phase error detector will be, if it's a XOR gate, it is going to be high for this much time, then low for this time, then again high here, and again low. And this is going to repeat every T time period. This is V times PD. Okay, so the output of XOR based phase detector, this is called as exclusive XOR PD. Okay, this is one of the digital phase detectors. Is high and low for the time proportional to the phase error or delta T. So if I, let me just call that this is amplitude A and this is amplitude minus A, whatever it is, you can say 0, A or something else. So if you look at it, this particular phase error detector is changing, means it does not have one single value. Okay, but the average of this phase detector, VPD average, will be equals to, you can say A times delta T minus A times T by 2 minus delta T, and average of T by 2. Right? So this is equal to A divided by T by 2 into T by 2 minus minus T by 2 plus 2 delta T. So this is A into 2 delta T over T, right? And minus 1. Okay, this is 4, right? So this is equals to, if I want to write in terms of phase, I have 2 pi delta t by t, so this is 2 by pi times delta phi phase error minus 1. Okay, now what is this phase error? Means if I look at what is the average voltage with respect to the phase error, delta phi with V average of the phase error detector output. Okay, so one thing you should be sure that this phase error detector output is not one single value, it's a waveform, right? It's a periodic waveform, but it has an average value, and the average value is proportional to the phase error. Okay, so for phase error equals to 0, this value is actually minus A, and the phase error equals to pi by 2, this is going to be 0, and the phase error equals to pi, this is going to be plus A. Okay, you can have A as 1 or whatever amplitude of the digital signals you are having, right? So it if you look at it, this is linear. Okay, so now look at it. Typically an XOR is a digital block which is a non-linear in terms of the input to the output characteristics, but the way we are using it, the average of the phase detector output is linearly related to the input phase error. Okay, now what happens on the two sides, you can plot it. The logic is this one. Okay, so now this phase error detector, if you look at the range, actually it doesn't go below minus A, so the range is, it has a linear range of 0 to pi. Okay, and what is the gain of this phase error detector? 2A by pi, right? So if you use this kind of phase error detector, it's quite easy to, means you can approximate at one single point, and the same gain stays forever. Okay? Yes?
So the frequency of these or that
No, we are not talking about the frequency error right now. We will look at it. This is phase detector, phase error detector. We are not looking at frequency error detector. Okay? So we will see what the problem is. It is doing that. Okay, that's why you see the range is 0 to pi only. Range is what? Yeah, so I want you to plot it if the phase error, if my input signal in place of coming here, if my input means if one signal is, let us say, like this, right? What happens? So you work out all the maths and you will find it is like this. Okay, I don't think this is that difficult to work it out. It's a linear expression. Okay, so let me stop here.